understanding. It could have been named human and machine understanding a contrarian view, because most of what I will be presenting is not in good compliance with the received opinion. So this beginning is kind of very opportune, because it runs against rules. I am honored to start this wonderful conference, and I want to start it. I want to start it by thanking our hosts for excellent arrangements and their very kind hospitality. So now to the subject of my presentation. Shall we dim the lights a little bit? It might be someone too bright.
No, it's okay.
It's okay.
So maybe you can switch on the light.
All right. So we start with an observation that over the last half-century, we witnessed the erection of a beautiful temple, this temple of science, of cognitive science and computational neuroscience. And all of that started from the intuition that brains compute their thoughts. But I think it should be better.
Is it okay or too dark?
No, it's good for me, and I thought it's better.
It's too dark. Oh, I'm
It's too
sorry.
dark.
Sorry.
All right. This intuition, brain compute thoughts, was very succinctly expressed by Paul Smolensky. And there are two basic notions here. That mental representations are distributed patterns of numerical activity. And the other one, which is underlined here, is this modification of connection strength, is the memory representation of the accumulated experiences. So these two notions are at the foundation of the computational neuroscience and computer science. If you give a closer look to this temple of science, you will notice a strange development. You will notice that a particular member of the family of psychology and philosophy, namely a theory of understanding, totally banned from cognitive science and cognitive neuroscience. Two pillars in this temple are unified theories of cognition by Alan Newell and volume on human problem solving by Newell and Simon. And you will find that in the unified theories of cognition, understanding isn't even mentioned. And in human problem solving, in 1,000 pages dedicated to human problem solving, where you would expect that the opening phrase would be that human problem solving is predicated on understanding problems, you will find that the notion of understanding appears first time and the last time on page 822, and in a very dismissive fashion. It says that higher level of mechanization can be achieved in executing algorithms without any evidence of understanding. So understanding is not necessary, neither sufficient for human problem solving, and that is a strange development in the cognitive sciences. Now, the thesis that I will try to advance in 12 minutes is that numerical activity is a very special form of conscious activities, and conscious activities are propagating along a very narrow path, among other, in the ocean of other cognitive processes, and these cognitive processes are neither conscious nor reducible to numerical representation, to computation. Now, the result of this expansion, generalizing from very small special case to the overall picture, assuming that all the cognitive processes are representable in the form of numerical patterns, is responsible, this over generalization is responsible for eliminating understanding from the picture of cognitive processes altogether. That would be my thesis. Now, if you assume the notion that brain compute thoughts, it commits you to a particular path in investigation. It allows you a very logical extrapolation that the faster you compute, the more intelligent your system would be. So this is from the web. It seems to be present, believed by Google, in the person Ray Kurzweil, that a human cognitive apparatus runs at a speed of 20 petaflops. And there are some other scientists that believe that that's not enough. Exaflop is necessary in order to compete with human level understanding in a machine. Now, the position that I'm taking would qualify this belief as an urban myth. And the notion is that you can move in a circle, accelerating the speed of computing as much as you want, and you will not get 1 iota closer to human level form of intelligence. You remain equidistant, so it's sort of on a different plane. 4 topics that I will address: what is understanding, why artificial intelligence and cognitive science avoid having to deal with understanding, some excerpts from the theory, virtual associative network, and a few concluding words about machine understanding. Obviously, within the space of a few minutes, I will not be able to develop any of these points, so it will be a very quick succession of highlights. What is understanding? Now, the concept of understanding has been central to philosophy since probably the time of classical Greece, which was 2,500 years ago, probably will be debated for another 2,500 years. So we cannot elaborate on it. A dictionary definition is that understanding means apprehending general relations in a multitude of particulars, so combining a multitude of disjointed fragments into coherent and cohesive whole. Now this cartoon would communicate pretty much everything that we need for this discussion to explicate the notion of understanding. This is obviously before the GPS was introduced. This is a driver who is asking a policeman for directions, and there was a very clear, understandable picture in the mind of the policeman, and in the mind of the listener, it's a jumble of disjointed pieces of information, a jumble of disjointed fragments, which do not make any coherent sense. So progression from this multitude of disjointed fragments to a coherent whole is what, in time, is what is accomplished by means of understanding. So progression from this picture to that picture to this kind of mental model is what we will mean by achieving understanding. So there are 3 basic notions here: multitude, coherence, and cohesive. I will not be able to define any of those, but I will look a little bit closer at some underlying ideas. Now, what's the benefit of understanding? What's the benefit of developing such an organized mental model in your mind? Well, there are multiple ones, and some of them are pretty obvious. If you have a well-organized mental model, it will allow you prediction, so you can envision what will happen in the future and how to progress. It allows you retrodiction. You can trace mentally your steps back and see what's been happening before, and allows you variation. Variation means that if there are unexpected obstacles, some eventualities that you haven't envisioned at the beginning, you are prepared to deal with them because you have a plan in your mind, you have a kind of map of the land in a sense, and this allows you to respond to unexpected eventualities. I will look at 2, in the next 2 slides, I will look at some underlying notions. 2 of them are pretty obvious, and the next one is less obvious, but much more important than previous. So you start with a jumble of unrelated components, which is an incoherent picture, and you proceed from incoherent to coherent. And this means that it's well organized, and while before you could have easily missed some of the components, when you have developed a coherent structure, then missing a component would become a noticeable event. Now, pieces get unified into a new structure, and this structure now becomes amenable to partitioning, which is not immanent in the organization that was there before. So partitioning is something that is possible on the coherent whole, new partitioning, but was not possible in the disorganized structure. Partitioning, for example, here means that I can identify geographical components, northeast, northwest, southeast, southwest. This was not immanent in the picture before. Now, the other part is much more important, and we'll concentrate on it a little bit more throughout the remaining, whatever, 7 minutes. Elaborate the notion of partitioning. You start, let's say, you take this area, this region. I can now contract it. I can say that there is northeastern district. I can contract it to kind of a point in my mental model, and I can contract it reversibly. I can go back, I can say, well, I am now in the northeastern district without looking into the elements of this contracted picture, just the label, and I can go back to the label. I can contract all the elements of this in this mental model, which will ultimately produce a structure, for example, like that. There is one cup, there is another cup. How many minutes left?
Nothing.
Nothing.
Only for 1 minute for questions.
Okay. Let me then proceed to the very last slide. For the very, oops. That was right. The last, if I get a little bit more time to develop, that would be the conclusion that cognitive science has concentrated so far on several forms of connectivity in the brain. One is physical connectivity, where neurons are in juxtaposition, so synaptic connections can physically develop. Functional connectivity is when synaptic connection develops as a result of exercise. And there is another form of connectivity which has been totally overlooked, relates to the organization of neuronal ensembles and manipulation of neuronal ensembles in conscious mind. This brings about a totally different mathematics and allows expression of what we call understanding in terms of manipulations of neuronal structures. But these manipulations do not involve changing in synaptic efficacy at all. So this is something that is, by virtue of not involving changing in synaptic efficacy, becomes reversible. Reversible operations that underlie mental modeling have been totally overlooked in neuroscience. It brings about totally different mathematics and different opportunities. And that will conclude my presentation. It was another thank you for a wonderful conference, but a very short one.
Thank you very much, Professor Yufik, for this talk. And maybe one question, at least. Any question? Okay, so we are in time, and thank you very much for your attention. So I will present Elsevier for saying you are. Okay, no, please, Sharon, you will say a few words about welcoming the meeting.
Okay, so welcome here. Thanks for being here. Sorry, it's a little bit of a strange start this morning, but I'm really happy to see you all here. Editors, associate editors,
Thank you very much.
scientists from the research discipline. I'm actually Sharon Buurmeijer, the publishing director of the physics journals, and I've known Paolo, who's not here, and Maurice already, I think, for 10 years or so. We meet in funny places in the world. But I'm really happy to see where we are with chaos, and I'm looking forward to an exciting day. And I think I give the floor now to you. And, thanks for being here.
Thank you very much. So I hope that we will recover Paolo soon. Meanwhile, he is in the police department. Ah, okay. So, So next talk will be Dr. Alexander Finkel-Kurtz about phenomenal consciousness as a high level of brain organization. Yes. Yes. I have a computer. The best is to put it with the next, with the talk of maybe Professor Calvo. Yeah. Yes, you will have the computer with you. Yeah. He will be the next speaker after you. Can you put use your computer with the USB key? Yes.
Of phenomenal consciousness as the highest level of the brain organization, and you see that this is part one. You should perceive it as an introduction to what will be presented by my twin brother in part two. So he will come after me and tell more details. So I will start with the working definition of phenomenal consciousness. Phenomenal consciousness we can regard as the highest level in the brain organization that captures all immediate and undeniable from the first person perspective phenomena of the subjective experience, such as hearing, touching, seeing, embodying and thinking, which present to any person right now and right here. And in this definition, phenomenal means subjective. Indeed, that any person possess subjective phenomenal consciousness if there is any type of subjective experience that present to this person at that particular moment. And this is in the frame of biological realism, which was introduced by Antti. And according to this biological realism, subjective or phenomenal consciousness is a real and natural phenomenon which is embodied somewhere in biological reality of the brain. And if this is true, then we have three propositions. First one, that if phenomenal consciousness is a biological phenomenon, then in the brain, then it should be some specific level of brain organization and some particular spatio-temporal pattern in this organization where consciousness resides. And please understand that I don't mean by saying this that we can localize consciousness in some particular brain area. All empirical data tell that apparently we cannot do this. But what I mean by that if we try to find consciousness, most likely we can find it somewhere in the reality of the brain than in the reality of out there. Second proposition, that we could expect on the lower, in comparison with phenomenal consciousness level of brain organization, that should be some non-experiential in form of some complex electrophysiological mechanisms, phenomena or functions which served as a direct realization base for the consciousness. And third proposition, that phenomenal consciousness should be, if it's a real phenomenon, then it should have some causal powers on biology. So in all these three propositions, you can see that there is a reference outside phenomenal consciousness. So what can be the explanatory models for consciousness? By and large, we can divide them on two groups: etiological explanation and the constitutive explanation. Etiological explanation, that is a backward looking, and we can distinguish three such pathways. Immediate causal pathway, that is a chain of events on the from the non-conscious or pre-conscious modulation of information to conscious and voluntary modulation of information. Examples can be, for example, the transition from dreamless sleep to awakening, or transition from loss of consciousness during general anesthesia to regaining of consciousness upon awakening from general anesthesia. Or it can be transition from vegetative state, which is characterized by no consciousness if it correctly diagnosed, to minimally conscious state or state with higher levels of consciousness. Or even in everyday prosaic situations like transition from automatic behavior and functioning to voluntary thinking and behavior. Third, second etiological pathway, it is developmental pathway, that is a chain of events from non-conscious fetus to full-blown consciousness. And according to cognitive neuroscience, the full-blown consciousness happened around 3 years old. And by the way, this event usually accompanied by very characteristic events in the human brain. And also evolutionary pathway, that is a chain of events from non-conscious organism to mammalian and human consciousness. And please notice that present form, state, and content of phenomenal consciousness, it always the last episode in any of these chain of events. And then we have second approach, constitutive explanation, which is a downward looking on the low-level constitutive mechanism of consciousness. And here we can distinguish micro-level neurocorrelates, meso-level, and large-scale level. And the whole totality of data from cognitive neuroscience and neuroscience and psychophysiology suggests that large-scale level, it is the level which can serve or which can contain the immediate lower level constitutes of consciousness. Why it's so? Because usually any changes in large scale neurodynamics are accompanied by changes in either form or state or content of phenomenal consciousness, and vice versa. The changes in state and content of phenomenal consciousness usually accompanied by large scale neurodynamic processes, but not so much, for example, with micro level. And just consider the simple fact that each day in healthy brain, thousands of neurons die. So this is affected micro level of neurocorrelates. But at the same time, you still have the same awareness of yourself. You have self-consciousness and consciousness of environment from day to day, which is not really very much vary in your capability to be self-conscious. So there is kind of not really much correlation between micro level and large scale level. Between the constitutive and etiological explanation of consciousness, there is one fundamental difference. Present form, state, and content of phenomenal consciousness can exist without any of these events of any of these chain present. Indeed, right now when I'm speaking to you, right here, my state of consciousness exists without any of these events present, because they are all in the past. At the same time, consciousness, even in principle, could not exist without constitutive activities. So if you chop out my head or affect it now with some pharmacology significantly, so you will see immediately the changes of my consciousness, or maybe it ceased totally. So it seems that if we want to explain consciousness, we need to look somewhere inside the brain. So what can be the appropriate neurophysiological level that captures consciousness? So we think that this should be immediately preceding level in the brain organization, which on which consciousness supervenes and to which consciousness is amorphic. And such level should have several requirements. It should be a complementary part of metastable brain-mind continuum. Metastability principle in neuroscience is a little bit different from the physics, and we understand it was introduced by Kelsa and in neuroscience. And we understand it as a competing tendencies, but coexisting together, tendency for autonomous regime of functioning with a tendency to integrative regime of functioning. Then this level should, the functional structure of this level should be isomorphic to the phenomenal structure of the mind, and the complexity of such level should be comparable with complexity of phenomenal structure. This because it is demonstrated that two systems can share the same information only in the case if they are equally complex. Then this level should have a nested hierarchical organization. Nested, it means that the components from the lower level, they constitute the components of the upper level. And there are no strong constricting control from the upper level upon the lower level. And the last one, this level should have relative independence from the neurophysiology itself. So can we find this level in the brain architecture, considering that actually brain regions and brain centers, they physically connected within the brain, but they do not represent physically nested system in the way as a cell nested within the organ. So in this way, it is not really clear what in the brain anatomy can represent or constitute a nested part of the hierarchy, which supports isomorphic, complex, and nested part of phenomenal world. So maybe instead of looking on the brain anatomical architecture, we should focus on brain functional architecture. We propose that brain operational architectonics, which is centered around the notion of operation, which is purely functional, it is the only brain level which require all, which satisfy all these requirements. And considering that operation is a process in time, they are present both in brain and the mind, and they have combinatorial in nature. So operation itself especially well suited to understand maybe how consciousness emerged from the brain activity. And we can distinguish relative complexity and compositionality of operations, and indeed that particular sequence of particular operations on the lower level usually constitute their kind of temporal bundle. So they constitute more complex operation on the more upper level, and so on until the highest level. In this sense, it is a purely nested hierarchy. So what we can find in the brain, what can be the nature of such operational architectonic with nested hierarchy in the brain. Let's briefly look what we know from the cognitive neuroscience, that simplest mental operations which are responsible for qualia of simple computations, they are presented in the brain in the form of local 3D fields, which can be measured nicely with electroencephalograph, for example, in the form of quasi-stable segments. So these local 3D fields, they are produced by transit functional neuronal ensembles. Why it is functional neuronal ensembles? Because functional neuronal ensembles, in contrast to anatomical or Hebbian neuronal ensembles, they do not need neurons in these ensembles. They do not need really to be connected physically, anatomically with axons. They are connected by the function. They participated in the same functional act, and this is very important. And transient, because they, again, to contrast to anatomical ensembles, they do not exist all the time. They exist as far as the operation need to be fulfilled. When operation is completed, these neuronal ensembles cease to exist, and neurons start participating in different neuronal ensembles. Complex operations, they naturally produced by the joining operations from different neuronal ensembles. And this, what we call operational architectonics, which is presented as a highly structured and dynamic extracellular electric field. And I'm now closing my presentation, telling that this operational architectonics, it's a level of working in operational space-time, meaning that when operation needs to be fulfilled, there is particular time for that, and particular neurons spatially distribute along the brain. This is why spatial temporal. And what is curious about this operational space-time, that by one leg it's standing literally in the brain, by another in the mind. Because operational space-time has emergent properties, which is, and by that it's a little bit independent from neuronal activity, and phenomenal space-time. It supervenes on the operational space-time with one-to-one correspondence, which is isomorphic to the operational space-time. So, and more details about this you will hear from consequent presentation.
Thank you very much. I propose to a few questions now. If you have any question about the talk, please.
Thanks. Thanks. It's not really a question, it's more a comment. According to you, according to your presentation, if I understood well, all the consciousness stuff is only related to the brain, but is there any place to the body, to the interaction brain and body? Because we know that coma patients, for instance, their brain is intact, but if you talk with any clinician, they will tell you that the consciousness level is probably different. So in your presentation, in your framework, which is very, very nice, but quite theoretical for me, I have the impression that you're missing the body. So is it possible to include the relation between body and consciousness in your framework in order to complete this consciousness aspects?
Thanks for your comment. Naturally, body is involved because brain controlling the body in a big part when the brain already developed very well. But body itself, it's not, to my point of view, it's not the main prerequisite for the consciousness to exist. But brain is the point where there is this connection between the virtual reality as a consciousness and the body itself happens. So it is in the brain. Speaking about the coma patients and vegetative patients, I actually studied them for several years. And we cannot speak about consciousness if we cannot have any information which we can objectively measure. And unfortunately, in coma patients, they are very difficult in the sense that they cannot give us any report about their subjective experience. If we don't know about subjective experience, we cannot speak about consciousness so far. I don't say that it cannot exist, but I'm saying that we can tell nothing about it from kind of using scientific approach. But when patients come into minimal conscious state, then yes, here we can already, we have a channel to communicate and to get information and even ask them if they remember something about coma state. But if you remember, for example, the work of Damasio, which described quite a nice episode when they have a lady which come out from the coma and they spoke with her, and apparently she regained very good memory about her state in the coma, and she was actually conscious about, according to her, about all environment and herself, but she did not have means to communicate. It's one story, but apparently, according to her, she even don't want to communicate. According to her, she did not have any motivation to communicate with anyone, so here it was some unusual emotional state. Plus, according to her, she had kind of emptiness of mind. So there was nothing to tell about it. So, but I think if we will proceed with studying this more, then maybe we will have more understanding how we can connect body there.
Okay. Any comment on the question also, or some? No? So I see that we have to start the next talk. And maybe we have to shorten it a little bit because we are delayed now, and because you are in the same spirit, so maybe you can shorten the talk a little bit.
I try, but my part is much more difficult because it's contained
It's more difficult, so you need more time.
No, I will not.
Okay.
I just would like to ask.
I suppose you have some symmetry in the talk, but you are not really.
Yes.
In this.
My point is that in my part of presentation, I will use some physical terms, but I am not a physicist. I am not a physiologist. So please forgive me if I use it loosely. And I understand that at some level it is a speculation, but this is how we neuroscientists try to introduce physical understanding into neuroscience. I believe that physicists who try to do neuroscience also do a lot of loosely usage of the neuroscience terms and neuroscience knowledge. But I think without this communication between different disciplines, we will never proceed further. So I will, based on what Alexander already told, I will just try to situate the phenomenon of consciousness into the physical reality, using these phenomena as criticality, self-organization, and emergence. And at the bottom of this operational space-time level, we see it, if we look from the neuroscience point of view, see a multiplicity of local extracellular fields. And the best way to measure them non-invasively, if we would like to study brain, we need to have some method which permit us to look inside without disturbing the brain. So one of these methods which can be used non-invasively to understand and to study these local extracellular fields is traditional electroencephalography, or EEG in short. And EEG waves, as you well know, recorded from the scalp are the result of self-organized behavior of the excitatory and inhibitory postsynaptic potential of neuronal assemblies. And since they reflect the extracellular currents caused by synchronized neuronal activity of many neurons, then they are reflected in the local EEG signal in the form of quasi-stationary segments, where each of such segments represents the envelope of amplitude modulation. In the literature, it is known as either common mode of wave packet or a standing wave. Naturally, the more neurons synchronize their activity, the more amplitude of this amplitude modulation. And if you look on this picture, I represent here one EEG derivation from the occipital left area, which is filtered in the alpha rhythm, in alpha band, from 7 until 13 frequencies. Why we filter the signal? Because different frequencies, they represent different temporal structure of the neuronal assembly's dynamics. So it has sense to filter them in a particular frequency band and then understand already the dynamics of these different temporal dynamics of the neuronal assemblies. So the amount of synchronized neurons within the neuronal assembly naturally tells us about the neuronal assembly size, and it represented in the average amplitude within the neuronal, within the quasi-stationary segment. As you see, this quasi-stationary segment, they change quite abruptly during these very short periods, which we call the rapid transitional periods. And the duration of the quasi-stationary segment, which is divided by these RTPs, naturally tells us about the duration of operation which neuronal assemble executes during each particular moment. So as Alex already told that these quasi-stationary segments, they're responsible for the simple phenomenal qualities or simple operations which produced by the brain. And the transition, which we can see in these RTPs, naturally tell us about abrupt switching from one neuronal assembly's operation to another. So physically, if we use the physical terminology, we can interpret these dynamics in the following way. So if we look at any two quasi-stationary segments separated by the rapid transitional period, then the previous stabilized period of the neuronal assemblies is formed to execute a particular operation which now this neuronal assemble need to be faced with. And this process is purely self-organizational. Nobody forces the neurons start to be active. But because of the phylogenetic and ontogenetic constraints, particular neurons, they are kind of predisposed to respond only on particular simple stimuli. So if the stimuli appeared in front of the brain, or it imagined during our phenomenological wishful thinking, then particular neurons which predispose to this simple stimulus start to be active. So they synchronized not by the anatomy, not by a particular center in the brain which forced them to be synchronized, but just because they self-organizationally respond to this particular stimuli. But naturally, during the time, the situation started to change, and there is a natural energy flow into the neuronal assemblies because they work out their resources. Blood need to bring new resources and also remove the products of waste. So, as we can see here, there is an increase of the entropy, and this process continues until it reaches the maximum level when the whole system reorganizes itself, and there is an abrupt decrease in entropy and organization of a new neuronal assemble, which now responding already on the new operation which the brain faces. And well, by my understanding of the literature in the physics, I gather that information and dimensionality should follow the same dynamics. In the physical literature, the phenomena similar to RTPs are referred as a renewal or critical or crucial events. Basically, the events that reset their memory, the memory of the system, so that the waiting times between such events are mutually independent. This was proved by the Allegrini with the co-workers. And this later property is in fact a mathematical definition of the intermittency, or the compatible with self-organized criticality in the physical systems. Recently, it has been documented that RTPs are indeed crucial events that correspond to the phase transition-induced criticality, and they have a power law distribution inter-event times. Again, it was shown by the Allegrini and Paradisi co-workers. Bax and Plants proposed to view such dynamics of local fields as the neuronal avalanches, which is analogous to the physical, to the avalanches found in the physical systems. And recently it has been proposed that neuronal avalanches are the signature of the brain which function near the criticality. Also, it was proposed that the sequences of avalanches themselves are organized again as avalanches. And if it's so, then we should expect a similar behavior already on the large scale, not with the formation of the separate neuronal assemblies, but at the higher level when the neuronal assemblies communicate between each other. And here we come to the macro level of the operational space-time organization. So again, as Alexander told, the simple operations, they are presented by the dynamics of the neuronal assemblies, but the complex operations of the brain are already presented by the synchronized operations of the several neuronal assemblies when they form so-called operational modules. And they are metastable in the nature because each of the neuronal assemblies even don't know that it synchronizes with some other neuronal assemblies, just execute its own operation. So it's kind of autonomous. But at the same time, because they temporarily happen to be synchronous with some other operation which produced by other neural assemblies, they already form this virtual temporal spatial module, which we call operational because it's synchronization of the simple operations. And the operational module already is responsible for the complex operation. If we look on the EEG, how this process can be measured. So if here we have a multi-channel EEG recording, which is already presented as a sequences of the quasi-stationary segments, which are separated by the rapid transitional periods, which marked here as vertical bars. And these RTPs, they are the markers of the beginning and ends of the quasi-stationary segments. Because they are the beginnings and the ends of the operations which neural ensemble produced, then synchronization of this beginning and ends tells us about the synchronization of the operations produced by the neural ensembles, which we measure in the different brain locations. So in this particular example, we have 5 EEG locations which neural ensemble synchronize their operations by synchronizing these RTPs. So the one immediate temporal moment when the RTP synchronized forms so-called the momentarily synchronous complex. So when the same set of brain areas again synchronize the abrupt change in the activity, so this will mark already the macro operation because it's the whole this structure, not the separate elements of this structure, is responsible for execution some more complex operation. For example, if we build in a house, there are different people who need to produce different functions. One need to deliver bricks, another deliver cement, another put cement, another put. There are a lot of elements which involved. So these all the separate neuronal assemblies. But their common task, their macro task, is to build a house. So you could not build a house if there are no elements available. So this is the same logic here. And in other words, the operational module, it is not a momentary synchronous complex. It is the whole temporal time during which particular set of neuronal locations, when neuronal assemblies exist, systematically synchronize their activity. Also, the simpler operational modules can be further synchronized and forming more complex operational modules. And they also separated, as we show in the experiments, between each other by the same rapid transitional periods, but already on the macro level, where the whole structure abruptly changed when the particular task, complex task, which subjects need to execute, abruptly also changed. And again, at this level, if we try to look at it from the physical point of view, we again see the same process, the same dynamics in the entropy, information, and dimensionality, where there is abrupt increase, and then the whole system reorganizes itself during the abrupt decrease in the entropy, information, and dimensionality, forms new complex structure, which now responsible for the execution of new complex task, which stays in front of the subjects. So that's basically all. Short conclusions that understanding of human consciousness requires the descriptions of the laws of the immediately underlying neuronal collective phenomena in the brain, which are reflected in the nested hierarchy of the spatiotemporal patterns of the 3D electromagnetic fields. And if we look on these dynamics, then these dynamics the same as we can see in the physical world, where the universal physical laws such as criticality and self-organization and emergence take place. Thank you.
Thank you, Ben.
ensembles are transitory. How can I gauge the time of their existence, and how would it relate to the manifested behavior? Manifested behaviors, minutes, hours, and ensembles exist for how long?
Ensembles really very fast. They exist within hundreds milliseconds only, like 200s, 300s, starting from 50.
Did anybody measure that?
There are some measurements with inserting multiple electrodes. Of course, they never manage to measure the whole neural ensemble, but at least the subset which they measure, they have these timings. But in our conceptualization, the behavior already corresponds to the large complex operations. And here already not separate neural ensembles, but the operational modules are important. And these operational modules, they can be from several seconds until hours, or I guess indefinite. Like, for example, the neural ensembles which support the default mode operation of the brain. And we show that those, they exist all the time. And their dynamic, of course, varies with time, but never dramatically. It never varies in the same way as the task which subjects confronted. So they exist during all possible activities which subjects execute. These particular operational modules which support the default mode system of the brain. So I guess that operational modules, it's this upper level which already more closer to the behavior which we can observe, like with the subject.
So what would be the neuronal substrate of this upper level? So at the low level, you have ensembles that exist for a very short period of time. And then at the manifested level, we have extended behavior for hours. What's the neuronal substrate that supports that manifested behavior? Other ensembles that persist for hours or more?
It's the same neuronal ensembles, particular set in each particular task, particular set of neuronal ensembles which systematically synchronize their activity. So each of these neuronal ensembles still continue to do their own task, but they kind of, and what is in between does not matter, between the beginning and end of the this micro dynamic. But what is important that the beginning and ending of each cycle which they produce, this quasi-stationary segment which we can measure at the EEG level, they all the time happen synchronously. And until they happen synchronously, this is the operational module. So it can be quite long. Can be several seconds, can be several minutes, hours, or as the default mode, we see it all the time. They never cease.
Okay, thank you very much. I think that we will now transfer the chairing of this session to Paolo.
You still the chair. Paolo is now.
Okay, so Paolo is no more chairman. There is a coup d'etat or something like
You
that.
are the chair for Paolo.
Okay, I will.
And then we change.
Okay. So now, Paolo, it's okay. Well, you agree of this transfer?
I apologize for being so late, and it's not totally my fault. I've been walking for about 1 hour looking for this place.
Yeah,
In the wrong
I
direction.
crossed you in Brussels, right?
I'm really sorry for that. And, so, but I will try to reduce my short to very short time. And so I hope that my work as editor is better than.
Somebody knows Apple? How to remove the other side?
For the session chaired by Professor Calvo, maybe you may use his laptop if you have a file on USB key. If you have it, maybe
But,
you can put it on his laptop. And maybe
Now we lose the chair after the talk.
Yes.
There are USB keys here,
I'll be the chair.
yes,
if you need USBs.
yeah, we can say.
Okay, good. So as I told you, I apologize for being so late, and I will try to reduce my talk that it was supposed to be to last for 1 hour, for half an hour. So first of all, I was supposed to welcome you, which is something that is too late for me to do. But I would like to say a few words about the main goal of this conference. The main goal of this conference actually is to do our best to improve the quality level of Solitons Fractals, and hopefully bringing it to a so big level as to become the leading journal of complexity. This is a very ambitious goal, but it's very difficult enterprise, but it's not impossible. And quoting what Stefano told me last night, I think if you imagine that the 30 outstanding contributors to this conference will promise and will maintain the promise of publishing, submitting to Solitons Fractals at least one manuscript a year, then that would be already a good level. And but I would like to stress the fact that, in my opinion, the idea of special issues is working very well, and there has been very attractive special issues, and the speakers that that you just did contributed a special issue devoted to criticizing the brain, which in my opinion was a successful issue. I would like also to mention a big achievement made by Matthias, who organized a special issue on evolution game theories, which turned out to be surprisingly successful. And I believe that we have to keep moving in that direction. And I think that I organize my talk in such a way as to give suggestions for possible new special issues. And of course, I should say that the problem of making the journal becoming a leading journal in the field of complexity is extremely tough and extremely difficult, also because there is a big, you see, the concept itself of complexity is not very well defined, and I believe that there are many different interpretations of what complexity is all about. And the idea of complexity that I'm trying to illustrate probably does not fit the point of view of the majority of the contributors to this conference. But that's not bad, that's good. That's good, because I believe that a debate trying to define better the complexity, which is, I would say, which in my opinion is science, means the progress of science. Everything else, now I might be nasty with other people, is engineering. But if you want to work in the direction of science, you have to keep moving in this direction, in the direction of complexity, and you have to, maybe you have to fight to define better this concept. Now, the that's what I'm trying to do. I'm trying to give possible suggestions. So the idea of complexity for me is connected to emergence. Emergence means something that results from the interaction between units, single units. They can be neurons or can be human beings, and to make a possible connection with game theory, I say some units must be cooperators, other units must be defectors, and criticality, which is one of the conditions that has been already mentioned in the earlier talks, might emerge from a special combination of the number of cooperators and the number of defectors. You see, I am very much interested in the concept of criticality that I have in mind has to do with which is the best way of which is the best manifestation of criticality. Here you see there are many people moving from Dante that think that criticality has to do with the emergence of a power law distribution of avalanches, and we think that is a very attractive view, but there is something that is not adequately considered, which is what they call temporal complexity. And temporal complexity is something that is connected to the concept of free will states. So the brain, or organized structures, they are, from time to time, they undergo collapses, and those collapses are a special moment where the role of committed minorities, to use a term that is popular among field people working on sociological applications, the committed minorities might drive the system. But this is changing completely the views of ordinary statistical physics. You have to move towards non-ergodic fluctuation. You have to invent a new fluctuation dissipation theorem. And I would like to stress also the fact that this might also lead to, since fractional calculus, that it is a field that apparently should be in that journal, our journal should be the journal where to publish fractional calculus, but you have to move toward the physical understanding of what is called fractional calculus. And now, let me, I think I will try to be more concise here. So, in this model, in the model that you are using, the single units have to make a decision on the basis of the nearest neighbor. So a given unit has n neighbors, and if n one of them are in the state yes, and n two in the state no, the guy, if the guy is in the state yes, might remain in the state yes for a longer time, and otherwise it must make a faster transition. And the defector should behave the opposite way. And it is interesting to see that if you study the mean field, you have that at criticality the mean field generates an inverse power law with mu equal to 1.5, and the behavior of the single units seem to be Poissonian, but if you look at more carefully at the single units, you find that in the time region with t smaller than 1 over g naught is the rate of the Poisson process, is the decay, the occurrence of events is faster, and then it becomes slower, which is something that can be easily explained using the concept of stretched exponential. You see, if lambda is very close to g naught and t is smaller than 1 over g naught, then if you replace alpha equal to 1, that is the property of an exponential with alpha with a number smaller than 1, you have a faster decay at short time and a slower decay at a larger time, which which makes the idea of stretched exponential very important. And the foundation of stretched exponential can be found in the work of Mittag-Leffler, that is not very well known, but you see, Mittag-Leffler defined a generalized exponential. When alpha is equal to 1, you have an ordinary exponential, and when alpha is more than 1, you have first a stretched exponential and then a power law. Now, I would say that, let me go very quick ahead. So the idea of stretched exponential, in my opinion, might serve the purpose of establishing a connection between what I call temporal criticality and the avalanches. Because you see, if you, in the top, you have a sequence of Poisson processes, and if the time distance between two units, suppose neurons, that are going to fire in the same burst, the time distance must become shorter, and neurons firing in different bursts tend to increase the time distance between two consecutive firing. And this is a way of generating avalanches, and at the same time what they call temporal criticality. This is the source of the Mittag-Leffler function tail. What is interesting to realize is the fact that the Mittag-Leffler function is closely connected to the concept of, so there are at this moment 1,000 papers devoted to fractional calculus, and people find that adopting the Caputo fractional derivatives, replacing the ordinary representation with the Caputo fractional derivatives, you can represent in a much better way reality. And according to the interpretation that emerged from our research work, this is because fractional calculus is, like a Mittag-Leffler function, is an emergent properties. Let me go very quickly to this paper that where we have established a connection. Well, the problem is why the Mittag-Leffler function is general, because there exists a new stochastic, a new central limit theorem that proves that the Mittag-Leffler function emerges as a result of a new central limit theorem. And this leads us to a totally different interpretation, or a physical interpretation of fractional calculus. And by the way, I would say that, and I'm stressing this because this might be an example of a new special issue, and a special issue devoted to fractional calculus, but with the condition that the author should emphasize the physical motivation. I mean, you don't accept papers that are merely algorithmic papers; they are automatically turned down. But if they establish a connection with the criticality, that's in my interpretation, anyway, with the emergent properties, they are very welcome, and I have in mind possible special issues that probably Paolo Allegrini will be talking about that in his next talk. And I have in mind also the idea of criticality is extremely important because it's possible to prove that if we adopt the idea of free will states, then the transmission of information does not take place as a result of information waves, but in a completely different way. And this is where I think that it might be nice to establish a connection with game theory. In fact, if you study our decision-making model in a condition of non-ordinary criticality, when the number of units is not infinitely large, and where we have free will states, then there is the problem that the time necessary to reach consensus is much faster than in the absence of cooperation. And an idea that I have in mind as a possible direction to follow in game theory is to imagine that suppose that the red guys are the terrorists, or maybe cancerous cells, and they will spread through our healthy society. And how a terrorist can convert an ordinary citizen, or a cancerous cell can convert a healthy cell. The idea of this possible new version of game theory is to imagine that when the red guy meets the green guy, you see you have to consider the mean field generated by people surrounding the green guy and the mean field of people surrounding the red guy, and what matters is which network reaches decision earlier. And then the red guy must become green or vice versa. So you might find directions to reverse the spreading of terrorism or reverse the spreading of cancerous cells. Okay, so that's all. I believe that I can stop here. I have in mind the possibility of organizing additional work on criticality in the brain, maybe additional work on fractional calculus connected to interpreted as emergent properties, and then, but for that you have to, I think that I'm not, you see, I'm an amateur. I think that I have to consult with Matthias. I don't know if the idea that I am illustrating makes sense or not, but this is a proposal. Yeah. Okay, that's it.
So, just one question, or if not, I have just to ask you about
yes.
What you have said about ergodicity, because for me, ergodicity in physics is very natural because it means that during some evolution the system will go from anywhere to any other way.
Yeah.
And therefore it seems to me natural that the complex system will explore all the possibilities. But fractional
but is a property.
calculus,
Yeah, but is a
so
property.
I have a very bad. Since I
No.
edited the journal, I received so many papers and very bad papers on fractional calculus. This disturbed my mind, but maybe you have to correct it now. Why this fractional calculus is contradicting the ergodicity? In my opinion,
Well, you are.
fractional
No.
Brownian motion.
Well, I would say that the
Best,
major, all the papers on fractional calculus that you are receiving should be turned down, and they are turned down.
Yes.
Because
But why you turn down also ergodicity?
no, I'm not turning down. Well, I'm saying that if you study, so in our opinion, the brain is not ergodic, and complex systems are not ergodic. In other words, I'm saying something that is trivial. It can be. There are many different ways of saying the same thing. There are people that contributed to the specialist on criticality. They imagine the brain as a system kept out of equilibrium due to a flow of energy, right? And that's another way of saying the same thing. So it is. So ergodicity is a property of equilibrium. The brain is not an equilibrium system. That's why. So in a sense, I'm saying something that is trivial.
There is no contradiction. There is no contradiction.
But
between ergodicity and the stationary in resting states. Resting states is ergodic in general.
Yes.
But if you go to evolutionary systems,
Right.
then it's much more complex, much
Right.
more involved in statistics
And,
probability.
And the brain is much more attractive. Is attractive to me because it's not ergodic.
Okay, there is no contradiction between ergodicity of stationary states
And so.
the evolutionary process.
And a work on fractional calculus can be acceptable if the author set the foundation.
Because in statistical mechanics, for example, non-equilibrium process arise also in ergodic stationary systems.
Yeah.
So there is no contradiction.
Okay. Okay.
Maybe quick question, but if you break ergodicity, don't you run into the risk of having divergences in the correlation functions?
Having what?
You might have divergences in the time correlation functions.
Yeah. And what is bad with that property? Is
you cannot define response functions then.
what?
You cannot define properly response functions at linear order, for example.
That's our job. In fact, you have invented a new fluctuation, that's what I mentioned, a new fluctuation dissipation theorem. You cannot use ordinary fluctuation dissipation theorem. I would be very glad to give you details, because you wrote several papers, by the way, some physical regulators on that issue. They are not easy, and, but in my opinion, they are a solution of the problem. It is possible. And not only that, but we also found an experimental check. I mean, that theorem has been checked experimentally in the Pisa lab with lead crystals. We found a surprising good agreement between theory and experiment. Using a new fluctuation dissipation theorem that is not ergodic. It's not based on ergodicity.
Okay, let's continue to the next talk. It's Professor Allegrini.
Okay, now it is me the chairman.
Yes.
Okay.
And then we have we will have a break.
Okay.
It's difficult to when you look at this.
So. I'm sorry.
I will use your computer.
Yes.
It's okay for you, and if it works.
You need your microphone. Yes. Sorry, your hand. Thank you.
I see that there is a problem here, but the plug is big enough.
You see anything? No. Me neither. Yeah. Can you hear me?
Yes.
Okay, let's do. Okay, I'm sorry. I was supposed to talk earlier, and so my presentation was structured. Having in mind that I would talk before the Fingerhoots brothers and just right after Paul. So I don't know, and I want to be shorter than I thought I was, because I think we are delayed at this point. So I will just move very quickly, and I want just to say that I will be moving, starting from what Paolo Grigolini has already said, that emergent properties, we're talking about the brain again, emergent properties in the brain have two kinds of complexity. One is a space complexity, that here I say network complexity. Another is a temporal complexity, which is normally overlooked by a lot of recent literature. But there is a lot of papers trying to connect this complexity, this emergence, to consciousness. What we did, since we are here to advertise the journal, what I want to say here is to go through the introduction of a paper that I published in a special issue, where I try to make a synthesis on the literature. Then probably I will not have the time to talk much about my original results, but they really are not that important. I will just go briefly to the meaning of them. But I wanted to say that for me it is important to use the fact that we sleep at night, and when we sleep we are not conscious. So we have a window to look at, where you can see if the complexity of the brain changes. So you have a correlate of consciousness, and you have it for normal patients, and you have it every night. Okay, and you can study it non-invasively with a standard EEG. In our case, we have high-density EEG at 128 channels, but it's not important. We can do everything also with the standard 1020 setup, because we are actually building on the Fingerhoots brother technology of looking at the rapid transition process. We will go. So the talk will just be the first 3 lines. Probably I will not talk about this, but I wanted to say what people in the neurophysiological community have reached, the consensus that have been reached about where we are in the consciousness science. Of course, I cannot give a real good synthesis because there are thousands of papers. But I wanted to select those ones where, as a physicist, as a complexity physicist, may enter and find the minimal synthesis we can get, at least from my particular point of view. And then, if there is some contrast, like Paolo said, it's good to bring it out. And then I will be talking about the indication we have that the brain is a critical, maybe, for sure, complex system, and how complexity and criticality may be exchanged one from the other. You have really an interaction between being critical in some sense and being complex in maybe a wider sense. And then I will be talking about some experimental results and bring some if when it's time you tell me to stop, but if I have time I will say that there is something strange going here in the connectivity, in the functional connectivity puzzles. There is a puzzle there, because my approach is the temporal complexity. Connectivity, functional complexity is a more mature field. We try to face the problem from a temporal point of view, but then we face some puzzle here. Let us see if we can get over that. Okay, so this is standard neurophysiological terms. What is consciousness? is a function that should state in the brain. Of course, there is also some connection with the body through some portion of the brains, but then this conscious state, what is when you are conscious, can be described with the qualitative approaches that have some properties. They have also a defect from a reductionistic point of view that they are private. It is very difficult to measure them. You have to rest on a speech report. And so this is another list that I found, probably in one of the finger quotes reviews, or maybe somewhere else. I don't remember where I found this list. This is a list. There are 16 properties that physicists should look at in order to explain consciousness. And you will see that I will be touching pretty much all of them, especially the number 3, the informative conscious content, the number 6, the limited capability, also number 5, the fact that you have internal consistency. Then we have to take into account also the subjectivity. So you really all that you can find, all that you can measure are necessary conditions for consciousness, but you never know if they are sufficient because you have the subjectivity to take into account. And then the stability, so Gestalt and things like that. So let's go a little back. Let's go from the beginning, Adam and Eve. Now this is just a cartoon. There is nothing really true in this picture, but people have asked where functions resides in the brain, because they have found a lot of functions, and even in recent years with magnetic resonance, you have found that a spot here is responsible for this behavior, a spot here is responsible for that other behavior. So you might think that also consciousness have a specific spot in your brain. But if you look, something so normal, just like being alive, talking, has to involve language, hearing, vision, movement control, and so you see that consciousness, a little thing of consciousness, it is everywhere. It's everywhere, but probably it's not saturating all the activity everywhere. Some portion of every part of the brain is participating in something, okay? And also motor integration. So the idea that there is something like a desk where that is not a normal function, but a meta function where something happens was the proposal of Barthes, 2002, when he invented the idea of the global workspace. So consciousness is there's something happening, you have a workspace, and the function resides over there, and they will participate in consciousness. And recently, Edelman and Barthes make Edelman, Nobel Prize. He has been writing about consciousness for a long time now. Have given some hint on what is this global workspace, because he worked a lot in these modules that arise spontaneously and are integrated nodes. Okay, and they said that there must be a specific integrated node that emerges as a global workspace. And then another big star talking about consciousness is Giulio Tononi. And Giulio Tononi says, well, we don't, and also following what Edelman have been thinking before, we have not to forget that there is a structure, there is anatomy in the brain, and you have all different regions with all different structures, all different connections, and say, yeah, it must be so, because to have consciousness, it does not have in mind what complexity is, because it is not coming from our disciplines. But it says that you need to have a critical, it doesn't say critical, but critical, interplay between being integrating information but also diversifying. Okay, and so that's what we try to make a synthesis in our paper, where figure 1 is just a mind map of consciousness, like this, where so you have these behaviors. It does this kind of box. So the critical point, and then at the end, the features that are explained by the hypothesis of the critical brain. And then in blue, you have the experiments that have been done recently, or not even too much recently. So the idea is that at the end you have complexity. A complexity is just an entropy reduction. That is, the whole is much larger than the sum of the parts. Okay, there is a cartoon way of saying complexity. And you have some people that are approaching the synthesis are here in this room, because the fact that at the critical point you have intermittency in fluctuation of the parameters was proved, for example, by Turalska et al. So if you look at this point here, you have those equations that Paolo was mentioning, where you have a phase transition, and then if you look at the time your excursion of the mean field goes up the zero level or below the zero level, you have temporal complexity, you have renewal. This is the aging experiment that proves that you have renewal. Then you might enlarge a little bit your vision and look at the correlational and functional connectivity, so the work of Bex and Planck, the fact that you have avalanches that have inverse power law, but also the fact that if you look at the correlation function and above a certain threshold, and then you do the adjacency matrix, you find a complex network, which is a scale-free network. This was a famous paper by Calvo, but also you can find the same also in the decision-making model. So this is what Paolo Grigorini has found. This is what Calvo had found a couple of years earlier. And so you see that here are an Ising model at the critical point in the supercritical and the subcritical regime, and here you have for the brain. Okay. So it looks like that for the brain, you really look similar to a complex system that might be critical, or the kind of criticality we have to think about that. But then one might also focus on the structure like Tononi does, and say that the structure itself is capable of giving you a complex behavior. For example, this is a work by Spohn. Now temperature is not changed, so here is just the normal Ising model, a critical regime, supercritical, subcritical. Okay? Here is just like a game life game, I don't know how it's. The coupling is the same, the rule of the game is the same. What changes here are the connection. In the first row, you have only nearest neighbor connection. In the bottom, you have all-to-all. Now in the middle, you have all-to-all. And if you do some complex network in the Strogatz way, you find exactly. So it looks like that the structure can be as good a control parameter than is temperature or coupling. So maybe that if I change the structure, if I make the structure more complicated, or maybe introducing inhibitory links, then you can have criticality. And this is a different kind of criticality, because the criticality which is broader than normal point-like criticality, which might be good for biological systems. And now let us go back to our work. That is actually, we moved from Fingerkurt's work in order to extract, because if you look at the temporal complexity, it's much easier, and we have theorems to exploit if you look at events, at crucial events. And the operational models of the Fingerkurts have been really a very nice technology to find crucial events. And what we found, okay, this is nothing more. Okay, we don't use their algorithm because we don't have their algorithm. We try to make something similar, probably but okay. It's not that important because the theorems that are exploiting are robust with some little changes. You don't find some, or if you find some noise. Then you have temporal complexity, so the usual autosimilar structure, and then you also have avalanches, in the sense that if you look at how many electrodes have an RTP simultaneously with a certain threshold, like Bex and plants do when they look at firing neurons, then you find an inverse power law, which is different from the usual 1.5, probably because in this case that you're looking at functional connectivity, so a structure which is not an all-to-all structure like, you know, when you go in a column, a microcolumn, or maybe also in functional, okay, I stop here. So when you are all-to-all, you can use a mean field theory, so you get 1.5 as an index. Here you find something different. That's what we get. And so what is true, we use all standard application to see if you really have these crucial events, and what you find is that when you are awake and when you sleep, in REM sleep, you really have what you imagine, but when you are in non-REM sleep, so when you are not conscious, then the curves bend, meaning that instead of having, you also have others. Instead of having one scene at a time, you have a simultaneous presence of more scenes at a time. Normally you have both, but when you are asleep, when the H index is 0.5, this one is lost. And so, for example, also the different modes that are in the default mode network, that starts behaving more independently.
The blue one is REM? Which was
This one is non-REM, but also the crosses, the purple crosses, that bends a little later. Okay, and also for the functional connectivity is the same, but the avalanches is the same. If you look at the avalanching, is the same, which I think we understood why. I don't want to. We think that Tononi will not agree because he made an experiment saying that it is not the same. We think we have the solution. Maybe that we can talk about that later. This one I wanted to show just to pay some credit again to Fingerkutz, because this is essentially a figure of our paper, but has been copied by some figures of their papers, and saying that's what happens. So this is the criticality, means circular back reaction and back reaction. So you have that elements get together, make bigger elements, but then those bigger elements with downwards causations puts some constraints on the little elements, and then over and over again till to reach consciousness. Okay? Now what happens during sleep? During sleep, that's what happens. It happens that a stimulus, in this case we used acoustic, tactile, visual stimulus, makes the same travel, these are different electrodes, as in wakefulness, but then you have a rebound, and you have a down state. So a lot of the brain goes in an electrical silence, hyperpolarization. So it means that no communication is possible. So the very same pathway that would lead to consciousness in sleep lead to quenching the whole brain. That's why you can have parallel computation, and that is maybe good for reprocessing memories, and that's it. Okay, these are new results, and then other stuff that I don't want to talk about because it's late.
So, is there? Okay, that's good.
Hold on. What do you think about the recent paper was published, I think, in Nonlinear Science, but probably you know from before, in which they measured the branching ratio during sleep, and they found that actually you can make a distinction between the state of the cortex when you are in REM sleep and non-REM sleep. And the bottom line is that I agree with Tononi's view that during REM sleep, there is some sort of pruning of synapses that were enhanced during wake state, and in summary, this particular state bring criticality down and balance the cortical. How that experimental result fit into your scheme of things?
No, okay, no, because to make a synthesis and explain everything, it's tough. But I think it should be okay. The paper you have in mind by whom?
There are 4 authors. One of them worked with, I don't remember the names. It was a postdoc with Tidmark
But
Lenz.
was it a paper that was using some connectome? No.
No. They measure EEG during sleep, and also in subjects that were deprived from sleep for many days. They look at the avalanching and the branching ratio, and they found that during REM sleep you sort of go from supercritical to critical.
Yes. Okay. I think I read that paper. There are so many, and so I got confused. Okay, that experimental setup of using sleep deprivation is a wonderful setup, and we also have to do some experiments like that ourselves. I think that this makes the network change, of course, with the huge with the sleep hunger, and that might also change the response that you have during sleep. I think that there is no really contradiction with what we found, because it depends also on the time scales you are using. Because if you look at a short time scale, you might seem to see the opposite behavior that you see when you look at the asymptotics. Why? Because if I say that when you are awake you have a more complex behavior, means that your diffusion coefficient, let's say, goes to infinity. So in a log-log scale you are moving very up and all down. Then at short time, or maybe that you are 0.5 but with a very high step, and then you have to connect. So in short times you might see something that is. I remember that this kind of paper was perfect from an experimental point of view, but I think that I thought that I could see that there was something in time scales. But we were looking at different time scales, so maybe that the results were looking. I think that we can match the results together. I remember reading it, I say, oh, there's something wrong, and I say, no, there's nothing wrong, and then I forgot, I'm sorry. We can go back to
okay. Are there other questions? Then you can stop here.
Yeah, so for now, so you can have coffee and some sweets. Yeah, so the break is going to be a little bit shorter, just 15 minutes.
How are you? Long time ago. Okay. 3 years. I mean, about 5.
I'm in Cambridge right now on sabbatical, right? I have a 1 year sabbatical. Yeah, they have this well, you can be there for 2 days. Yeah.